And I think, Linda, you can start.
Okay, thank you, Clara, for inviting me, and it's always a pleasure for me to talk a little bit about ANITA. Spoilers alert, you know, the parallel universe things was mainly a tabloid, more than a real results from us, but we'll get to there in a little bit. So a bit of an outline of what I'm going to show about today. I'm going to start with some motivations as to why we want to go to Antarctica to look for neutrinos. Then I'll talk a little bit about the ANITA experiment in general. And then our two main analyses, which are the neutrino search and the cosmic ray search. And then at the end, I'll talk a little bit about what's in it for us in the future. For the cosmic ray analysis, what we're actually going to see are super new results because we were presented at Neutrino 2020 just a couple of weeks ago. So first of all, some motivations. So why do we want to go to Antarctica to look for these neutrinos? And what you can see right here is a picture of some ANITA collaborators just outside McMurdo Station, where there's these pressure ridges. So pressure ridges are ice formations that come from when the sea ice collides with the permanent ice shelf. So you will have like a little bit what happens when you have an earthquake and the mountains form. And the same thing, but with ice. So they're beautiful. So why ultra high energy neutrinos? So if we think of a very simplistic sort of picture of the universe, we have a source which is really far away from us, and this source is producing different particles. We have our protons, which, let's start with the photons actually. Your traditional astronomy, we think of this person looking through a telescope, looking for photons and like these particles of light. But then we can think that something as thin as a sheet of paper can actually stop the photons. So anything, any dust, anything that is in between our source and us will stop the photons. Then let's say our source is producing protons. Protons can travel through dust and can reach the Earth, but they can also be deflected by magnetic fields. So by the time we get to the Earth, it's a little bit more complicated to point them back directly to where our source was, especially if we have uncertainties on the magnetic field during their path. Neutrinos, on the other hand, can travel basically completely undisturbed through extremely long distances. So they're the perfect tool to study sources really far away from us and bring us information from the most remote corners of the universe. And one of the reasons, so the neutrinos that we're looking for are neutrinos that come from cosmic rays interaction. So cosmic rays, we've known them pretty well. We've been measuring them for decades, and you can see here the spectrum of cosmic rays, which is pretty well measured over 11 orders of magnitude. But in the high energy here, above 10 to the 19.5 electron volts, we see a cutoff. This cutoff comes because the cosmic rays start interacting with the cosmic microwave background. And if our cosmic rays are mainly composed by protons, then by interaction with a gamma, we have a delta S and then pion decay into various flavors of neutrinos. If the cosmic rays are composed of heavier elements, then at that point we still have a neutrino flux produced, mainly antineutrinos, and the neutrinos still get quite a big fraction of the energy from the cosmic rays. And that's where this cutoff comes from. So the neutrinos we're looking for are neutrinos that come from this GZK cutoff. An additional reason to study, of course, this type of neutrino is, as I said at the beginning, to do neutrino astronomy. And we've heard quite a lot about this specific Texas source in the past couple of years. IceCube identified 13 very high energy events, astrophysical neutrinos, in the direction of a blazar, and this could suggest that blazars could accelerate cosmic rays to the highest energy. But of course, we need a lot more detections to verify this. So if I gave you a few ideas as to why this is interesting from the astronomy side, from the particle physics side, we need to think that if you have a neutrino, an ultra high energy neutrino that has energy above 10 to the 18 electron volt, and is colliding on something static, the center of mass energy will be like huge. I think it's 300 TeV. I wrote here 300 TeV, but I think that's for an E219 neutrino. But you get the gist of how that works. And from a particle physics side, that's extremely fascinating. There's of course more motivations, and when you have these. So going high in energy means also like neutrinos coming from further away. So traveling longer, there will be implications for neutrino mixing. What do we see? Do we see neutrinos in free fractions of electron neutrino, mu neutrino, and tau neutrino that are perfectly the same, or something different? At this energy, we can have neutrino decay, so neutrino decaying into photons. They were, of course, one can measure then ultra high energy neutrino cross sections. I'm a cross section person from my NOVA side mainly, so I find cross section extremely fascinating, especially at these really high energy. One can put limits on Lorentz invariance as well. And then there's these 3 additional bullet points of sterile neutrinos beyond standard model and dark matter, that these are all related to the mysterious events that we found in ANITA 1 and 3. And I'll get to them a little bit later into the seminar. So hopefully I motivated you enough as to why this is an interesting field and interesting things to look at. So here now I'm going to talk a little bit more about the ANITA experiment. And here's a beautiful picture of ANITA 4, which is the last flight we did, which was in 2016. And the ANITA collaboration is actually quite a small collaboration, especially if we think of, collaborations like DUNE, that is 1,200 people. ANITA only has 50 collaborators. And you can see here an outline of Antarctica. And the reason why I also pointed at all the institutions that are part of our collaborations is also because of a convention that we have when we talk about Antarctica. So the South Pole is of course south. Every place is it's not the South Pole is north. And then we would talk about East Antarctica, the bit of Antarctica which is closer to the east. So you can see right here that we have an arrow towards University of Taiwan. And West Antarctica, the part of Antarctica which is closer to South America. So you can see here the arrows that point to the various American institutions. So ANITA stands for the Antarctic Impulsive Transient Antenna. And the concept of the experiment is that we have these radio antenna array attached to a giant helium balloon which flies above Antarctica. So right here I wrote 40 kilometers in altitude. That's because that's the altitude that ANITA flies at. So attached to this giant helium balloon, these radio antennas look down and then look for an ultra high energy neutrino interaction. So when a neutrino, we look for Earth-skimming neutrinos, it will interact with the ice and produce Cherenkov light, which you're probably very familiar with. But together with Cherenkov light in the ice, we also have Askaryan emission. So you can think of Askaryan emission as like the radio cousin of Cherenkov. It's a coherent emission in the radio frequencies. So we have this coherent emission in the radio frequencies, which then gets propagated all the way to ANITA. And because of the geometry of how this interaction happens and how it's then refracted from the ice to the air, we can say that neutrinos have mostly a signature of vertical polarization. I forgot to mention one thing here, which is 40 kilometers is, if you're not very familiar with how high that is, When you're flying on a plane, you're about 10 kilometers. So ANITA flies at 4 times the altitude of a plane. And this is why we're partnered with NASA, which is actually, so what we do is we put the detector together, but then the launch is then, for the launch, we give the detector sort of to NASA that does the launch for us. So a few words about Askaryan radiation if you're not familiar with it. So it's a coherent radio emission from an electromagnetic cascade in a dielectric. So it means it works well in ice, it works well in salt, but it might not work as well in other materials. And the ANITA collaboration actually measured Askaryan radiation for the first time in 2006. So we had a test beam at Slack, and you can see in these pictures here, we had a big block of ice, 7,000 kilograms of ice, and then it was fired with bunches of electrons at almost 30 GeV. And here, the bluish light that you see, just your chunk of light, which will be bluish in what's it called, in ice. And then we had a prototype of the ANITA detector in front of it to see the coherent radio emission, which was then detected for the first time. There is a second signature that ANITA can look at, and that's can look for, and that's cosmic rays. So let's look at first the left-hand side of this picture. So ANITA can see direct ultra-high energy cosmic rays, and these are interaction in the air. So we don't care about the ice. The ice is there, fine, but what the cosmic rays care about is actually the air. So we will have a cosmic ray shower coming towards ANITA, like in this case, but we need to remember that ANITA flies in Antarctica, so very close to the South Pole. So the Earth magnetic field is vertical, pointing downwards. And so the interaction of the air shower with the magnetic field creates a charge imbalance, which then becomes a horizontally polarized radio impulse. So a cheat sheet up here is that for us, neutrinos are mostly vertically polarized and cosmic rays are mostly horizontally polarized. There is a second signature of cosmic rays, which we can see, which are reflected cosmic rays. So if you have our angle to actually see direct cosmic rays is pretty small, because the ANITA antennas are pointed downwards. So direct cosmic rays will come at a shallow angle. So if this is our horizon, direct cosmic rays will only come from the horizontal to maybe here. But we have a much larger angular acceptance for reflected cosmic rays. So these are cosmic rays that come at a steep angle, get reflected off of this, and then towards ANITA. So these are the two main signatures that we look at. So now let's take a closer look at the instrument itself. And this is a picture again of ANITA 4. And the white thing that you see right here, these are radio antennas, and they can detect radio frequencies in the horizontal and vertical polarization. While ANITA is flying, it needs to get power, and that's why we have all of these solar panels at the bottom and at the top. And again, while it's flying, it's really important that we can communicate with ANITA. So this orange antenna right here and the big blob right here, these are two satellite antennas, Tigris and Iridium, which is what we use to communicate with ANITA while it's flying. So it's quite nerve-wracking to think that you put together an experiment and then you let it fly over Antarctica, and then you actually have very little control over it, because since we let it fly, we can't control where it's going, but we can have some small information about how things are going through this communication. And to give you a sense of how frustrating it is sometimes is, if you remember the first internet connections of the 90s, the speed of connection we get is about 10 times slower. So we actually only have a limited amount of information during flight. Then we have our GPS antennas, because we need to know where ANITA is and also how it's oriented. And then you can see all of the cables and electronics all go to our instrument box, which is where we have our PC and the main electronics. This is just a short GIF to the dimension of ANITA are of this sort of payloads are constrained by the launch envelope, so they can't be any bigger than from here to up here. So to be able to add an additional row of antennas, we did this short mechanism in which during launch the solar panels are up, and then once it's flying, the solar panels drop down, and that's, as I said, is just to get more antennas in. So now I'm going to show you a short short video of the launch. This is an accelerated video because this is a balloon. So although it's very exciting to be there, and so here you can see ANITA, and then the cord to the balloon. These are people, so that it tells you how big the balloon is. So although it's really exciting to be there, so so these are all NASA riggers. So we're not allowed to be close to the payload during launch for safety reason. So we had radios to communicate with the NASA riggers. So we got the whole, if you want, NASA experience of having like, okay, 1 minute to launch, 30 seconds to launch, and then the countdown. But then in the end, it's a balloon, so it actually goes pretty slowly. And here you can see a sort of very accelerated video. All of it was about 4 or 5 minutes. And you're probably wondering, why isn't the balloon fully inflated? It is fully inflated, it's full of helium, but we need to remember that we put the helium in at altitude basically 0, and then ANITA flies at 40 kilometers. And so the pressure of the air of the atmosphere is very different at 40 kilometers. And so by the time it gets to 40 kilometers, it expands completely, and it gets really, really big. It's as big as a football stadium when it's fully inflated. And here are some pictures taken through a telescope. Right. So this is the flight path. Then we launched ANITA 4 on at the beginning of December in 2016, and then it followed the polar vortex, as you can see right here. So the polar vortex blows anti-clockwise every year in Antarctica. So ANITA follows the polar vortex until the end of the flight, which was about almost a month later. And the reason why we stopped the flight was because ANITA was close to what we would call a convenient location, which is probably one of the few times we will ever talk about 125 kilometers from the South Pole to be a convenient location. And the way the flight stops is quite actually dramatic. We have a small explosive at the top of the payload, and NASA has a big red button, something like a big red button. And when we decided we want to end the flight, our PI called NASA, and we press this big red button. So the explosive goes off and effectively cuts the cord to the balloon. The balloon then falls for 40 kilometers with a parachute, but it's still like a pretty hard fall, as you can see in this picture. So what we do straight away, this was like 10 days later, and we go there and pick up our hard drives, because I told you earlier, we let the experiment go, but we had very, very little information about what's happening. So in some ways, we don't really have our data until we go and pick it up. So we have 3 hard drives which were picked up straight away 10 days after the flight finished. And then we did a full recovery in December 2017. So in December 2017, a small team went back to Antarctica, dismantled it, and then bit by bit brought everything back. Because of course you cannot litter Antarctica with your old particle physics detector. So there's been 4 ANITA flights so far. There was one in, ANITA 1 was in 2006-2007, ANITA 2 was in 2008-2009, then ANITA 3 was in 2014-2015, and then ANITA 4 was in 2016. I'm mainly going to talk about ANITA 3 and ANITA 4. This is just because they were the latest two flights, and of course the most sensitive ones. So I talked a lot about how the experiment works, and I don't know, I'm not really sure how many of you are actually familiar with radio detection. So radio detection works quite differently than light detection. So each of our radio antennas sees a waveform, and so here is an example of what is an event display for us. So each of these waveforms traces back to one of the white antennas I showed you earlier, and here these waveforms are red because they were the channels that had triggered. So the way our analysis works is that we perform cross correlations. So you go on the Fourier domain and cross correlate all of these channels to find a map. And one way of thinking about it is figuring out at what time this peak was in this channel and the peak was in that channel, what time was in this channel, and so on and so on, to figure out where the impulse came from. So from this event, we can perform all of the cross correlation and then make an interferometric map. So make a map of where our impulse came from. In this case, this map is on the x-axis, we have a payload phi, which is the azimuth, so it's going horizontally around, all around the payload. And then on the y-axis, we have the elevation, which is goes from up and down, or goes up and down. And then we can also then produce a zoomed map to see closer how the peak sort of developed. Having then information about how, so once we have this sort of maps, we have information about where the payload was and how it entered, so we can point it back either to Antarctica or to the universe. So hopefully now you have a sense of how the ANITA experiment works. Now I'm going to talk a little bit about the analysis. I like to think about looking for needles in a haystack, but I guess it's a little bit like that in all particle physics analysis. So I'm not sure how much of this picture actually renders through Zoom connection. But so this is McMurdo Island, which is where McMurdo Station is. So if you see some black sort of dots and lights here, that's the airport. So when you're flying to Antarctica, you fly, so in our case, when you fly to McMurdo, you fly from New Zealand. So you land right here on a compact snow landing. And then if you can see like a few black dots right here, that's what we would call the office. So this is where we put ANITA, and this is where we then launched it. This is because it's unsafe to do any of the work of the payloads closer to human settlements. So even though we were in Antarctica, we had a sort of like a 45 minutes commute every day to go there and work on the payload before the launch. So what's the challenge here? So we have about 100 million events per flight, and maybe a few neutrinos in there, and tens of cosmic rays. And so that's probably normal for particle physics analysis, with the additional challenge where we don't really know what our source is. So the signals, because these neutrinos have never been detected, then it becomes slightly more complicated. So let's talk a little bit about the backgrounds. So the things we know well of and the things we need to get rid of. So one of our biggest backgrounds is actually humans and satellites talking to each other. And they like to do that on two frequency bands at 260 and 380. This on the left-hand side, you can see a plot with the power spectral density of 1 minute of our data set. So on the x-axis, we have the frequency, and on the y-axis is what would be something like the power spectrum. And you can see very well these two peaks, and these two peaks are like people talking to each other on walkie-talkies and satellites. Actually, the walkie-talkies bits is more the 260, the 380 is mainly American satellites. So how do we get rid of this? So you'll be surprised, but these satellites weren't up during ANITA 1 and ANITA 2. So in ANITA 3, we had this like beautiful sensitive experiment, and then we launched it, and suddenly we realized that there was all these satellites talking. So it was too late for us to get rid of them in hardware, so we got rid of in software. Whereas for with time subtraction algorithm, and whereas in ANITA 4, we had time to actually think about what we knew that ANITA 3 had them. So we developed some filters to go right at the antenna to actually get rid of them. Oh, I forgot to talk about this plot on the right, which is also from ANITA 3. And it shows you again how bad is the background coming from satellites. So on the x-axis, this is time. So that's December, 21st of December, 28th of December, 4th of January. And then on the y-axis is the highest peak that we can see, the direction of the highest peak that we can see in each of the map that I showed earlier. Sorry. So these big stripes that you can see right here, these were satellites that were just flying and orbiting, above ANITA. And you can see them really, really well. We had to get rid or find a way to get rid of them. The second thin slices you can see here, and these ones, they have a period of 1 day, so you can guess that's the sun. And well, you know, we can't really get rid of the sun. Nobody would like that. So the vast majority of ANITA events are actually thermal noise. So we use Fisher discriminants based on impulsivity to get rid of those. And so here you can see the performance of these Fisher discriminants compared to our simulated neutrinos, as well as calibration pulses that we took during the flight. So finally, we're left with about 500,000 events. And then what we do is we need to make sure that these events don't come from humans again on the continent. If you want to know what a neutrino kind of looks like for us, or a cosmic ray kind of looks like, it looks like a piezo, basically. So if you have a lighter, that will give us a very similar signature to a neutrino or a cosmic ray, depending on what polarization your lighter gets it. And so what we need to do is make sure that none of our signals come from humans. And so we have a list of human bases of all human activities that happens in Antarctica. So we point all of our all of our events to Antarctica and remove anything which clusters with human bases. And then we also assume that if there's 3 events that come from the same location in Antarctica, then at that point either some human activity that we didn't know of, or there is some other activity that, again, we didn't know of and produce that. Because it's very, very unlikely that we have more than 3 events coming from this direction in Antarctica, given that that will be not exactly the same direction then on the sky. So once we do all of that, and for our neutrino search, we actually left with not much. For ANITA 2 and ANITA 3, we were left with 2 events in total, were consistent with our background estimation. So we put the most stringent limit on ultra high energy neutrinos at from 10 to the 19.5 sort of electron volts and above. Lower energy and Auger and IceCube are more sensitive than us, and the main reason for that is because they're on with time, and that's one thing that we can't compete on, which is exposure. Our exposure is always like 30 days at a time, one month time. Oh, okay. For some reason, I lost a picture. That's fine. So now I'm going to talk about our cosmic ray showers. And so for detection of cosmic rays and the cosmic ray analysis is very similar to the neutrino one, but we know what a cosmic ray signature is. So we can actually make searches with much lower background estimations. So as a sort of reminder, the direct cosmic rays come from the shallow angles, so from the horizontal to the horizon, whereas reflected cosmic rays can come at steeper angle because they get reflected off of the ice. And what I didn't tell you a lot about was that we can actually tell what ray is direct or reflected. This is because we can look at the plane of polarization. So here is an example of some cosmic rays that we saw in ANITA 1, in which you can see that all of the reflected cosmic ray were going up. The pole was, the first dominant pole was positive. Whereas, sorry for the reflected, yes. Whereas for the direct cosmic rays, the dominant pole, and the first pole was negative. And that's how we can tell. Another thing that you can look at is also the relationship that you can see from the polarization angle that we measure from these waveforms and the magnetic field of the Earth in that specific point, because we know exactly where we detected our, we know where we detected our event. So you can look up of what the magnetic field direction was in that specific point of the Earth. And then you can correlate it with the polarization goal. And it's very clear that in both ANITA 1 we show a clear dependence. So we saw quite a few cosmic in the different flights. If you're wondering why ANITA 2 only detected 2, this is because it was a serendipitous, weren't expecting to detect cosmic rays in ANITA. So when we saw cosmic rays in ANITA 1, we thought it was background. And so we turned off that trigger to little we knew that they were another physics signature. So when that was then turned back on, and in ANITA 4 saw quite a big fraction of them. So you've probably heard a little about our mystery events. So these are events that cannot be explained with our current of the standard model. So I'll talk to you about direct cosmic rays, and I'll talk to you about reflected cosmic rays. And here you can see examples of some of the waveforms for direct and reflected. So what you can see is the indirect case, the main pole is negative, and in the reflected case, the main pole is positive. So here I'm just giving you a very qualitative description of you know, look at the main pole is positive or negative. What we actually do is measure the polarity of the event. But what we found for the let's go back 1 second to these waveforms. The other thing that you notice is that for the direct events, the angles are very small, they're very shallow, -4, -5 degrees. Whereas the reflected events, of course, have a much steeper angles, -37 degrees in this case. So 2 mystery events that we found, one was in ANITA 3 and one in ANITA 1, were things that we couldn't really understand. So we have the polarity, which is consistent with a direct event. So right here, the main pole is negative, but it comes at a very steep angle. So in this case, -35. So it's steep and it's direct. So why is that weird? So this could be a signature of a tau neutrino. Very interesting, yes. But at this steep angle, 35 degrees, it means that to come up at 35 degrees, it should have traveled for 6,000 to 7,000 kilometers through the Earth. Now, I don't know how many of you are familiar with neutrino cross sections, but which basically go with neutrino energy. And at this sort of energy, no neutrinos should have survived. The interaction length of neutrinos at 1 eV is 1,600 kilometers. So it shouldn't have survived this very long chord length. But what's more interesting, even more interesting than that, is that there's current standard model particle that would have survived length on the Earth. And the background estimate of this analysis is 10 to the minus 2. The reason why the background estimate is so small is because we know what a cosmic ray looks like at this energy. Like Auger has seen plenty of cosmic rays at this energy, so we know the signature, and we can make analysis in which the background estimate is much smaller. So you put out these papers, and of course they get up by, well, actually first we get loads of, what's it called, phenomenology papers trying to explain them. But then they also get picked up by some of the tabloids and some of the news. So you can see some of the articles that came out. Bizarre particles keep flying out of Antarctica's ice and they might shatter modern physics. Wow. This parallel universe thing was related to a paper actually from Ankerdoki et al. Where was trying to explain these events using the CPT universe. And so it was again saying like these events might be caused by axions from the core of the Earth actually. And again, other weird signals in Antarctica, new realm of physics. Anyway, all news is good news. I don't know. So what's the problem with various interpretations of these events? So if these were tau neutrinos, one big question that we've had is why hasn't IceCube seen any of them? So what you can see here on the left is our acceptance as a function of energy. And ANITA is both in blue and red. So red would be our Askaryan tau search, and blue would be the air shower search. So while we have really good acceptance with respect to Auger and IceCube, what I was saying earlier, the exposure which you get by multiplying the acceptance by how long your experiment has been running is of course much higher for both Auger and IceCube, because Auger and IceCube are just on the whole time, whereas we only fly for 30 days. So big question, why hasn't IceCube or Auger, haven't IceCube or Auger seen these events? And the second big is actually related to self-consistency between ANITA and itself, which is, right, we're seeing two events at these very steep angles, but our acceptance is much larger at shallower angle. So why are we seeing events at this very, very steep 35 degrees and not at 20 degrees, not at 10 degrees, where the neutrinos should have traveled a lot less and through the Earth, and it would have been much more likely actually to see them. So these are actually these are questions that make the detection a lot more difficult. So there were of course lots of interpretations. As I said, there was a sterile neutrinos interpretation in which these events could be explained by the fact that the cross section of sterile neutrinos is suppressed by theta square. But again, we would need a part of, there's still the question like, why hasn't IceCube seen them? And similarly, there were other papers talking about the decay of massive dark matter candidates into two right-handed neutrinos, which could have explained this, beyond standard model particles and so on and so forth. But again, there's always this big question, why hasn't IceCube seen them, or why at such a steep angle and not shallower? So these are quite difficult interpretations, and for a long time, what everyone wanted was to hear what was happening with the ANITA 4. And finally, what has ANITA 4 seen? ANITA 4 has not seen this type of events, and what has ANITA 4 seen is something slightly different. So we've seen 4 direct events, but at this time at a much shallower angle. So I'm sorry, so here the convention is slightly different. So this is theta with respect to the horizon. So the 0 would be the point in which the horizon is. So these are like below horizon, so direct events, but they're very shallow with respect to the medium energy, mysterious events that I showed you earlier. So what has ANITA 4 seen is a total of 29 showers, the vast majority of them are consistent with the geometry that we expect them to be. Only these 4 ones here are inconsistent with the geometry. But again, these are much shallower in angle than the very steep ones. So what's our take on the so what does this mean? It means that at least ANITA 4, we cannot see any steep events inconsistent with polarity with what we've seen in ANITA 1 and ANITA 3. What matters is that those 2 events might have been just something more mundane, like our understanding of space might be more complicated than we would currently know of, and maybe some weird ice geometries might have generated those. So as I said, these are like results which are the ANITA 4 results are pretty new. They were presented 2 weeks ago at Neutrino 2020, and we're in the process of writing a paper which should be out probably in the next couple of months. So what's in it for the future? So there's different experiments looking at the future. One is ARA, and if you haven't heard of ARA, you can think of ARA as the baby child between and ANITA. So you've got the radio antennas, but they're buried in the ice, and and ARA is quite interesting because it sits right in between the energies of ANITA and IceCube. So here you can see what IceCube is, which is 1 cubic kilometers, and then this is the full size of ARA. And at the moment, there's only 5 stations that have been built. So we have 1, 2, 3, and I think this is 4, and this is 5 stations currently built. So ARA can access these like really large volumes and hence get higher in energy than IceCube. And the nice thing about ARA is that it won't have ANITA's problem, which is exposure. So ANITA only flies for a month every few years, whereas ARA will just be on continuously. Still on the payload though, sort of upgrades, and the ANITA upgrade will be a payload called Pueo, which is also the name of a Hawaiian owl. And the idea will be pretty similar to what we have currently in ANITA, but we're going to be using more antennas at a larger, with a different type of triggers. So the maps that I showed you earlier, so a new trigger will be able to create those interferometric maps on the fly. And additionally, what we're adding is a radio array at the bottom, just for looking for this steep events, or to look at, just to look specifically at events. So as a summary, we have a rich physics program. I showed you the ANITA 3 and ANITA 4 diffuse neutrino analysis, and also the ANITA 3 and ANITA cosmic ray analysis. I didn't cover quite a few things. I didn't cover our simulation, of course. We have a program with a calibration source which actually flies just behind ANITA. This is HiCal, and it gets launched a few days after ANITA. We have specific source searches. These are still these are not out yet for ANITA 3 and 4. They're going to come out again before the end of the year. And I'm going to leave you with a picture of our last collaboration meeting. Thank you.
Thank you, Linda. I enjoy a lot the seminar because you perfectly described the technical challenges and the interesting results you get. I think now we can proceed to questions. Juan already raised his hand. Juan, you can ask.
Yeah, hello, Linda. Very interesting seminar. I'm not going to ask you about the science. I need magic, so you don't have to convince me that this is a very interesting stuff. But I ask you about the the technique itself and maybe the background. But maybe I ask you first about the exposure. You've been saying again that it's only 1 month you get. And I was wondering, why cannot you extend? I mean, the balloon will go around and around and around, right? This is trapped in the vortex. I was wondering, why can't you use all summer and wait for 3 months or something like that?
So various reasons. So NASA has a long history of doing this sort of balloon, long duration balloon experiment. So every year there will be a couple of these that get launched. In all of its history, the longest flight has been 45 days. So longer than 45 days, it's basically impossible. And 45 days was a payload called Super Tiger, which was looking at cosmic rays. And the reason why longer than 45 days is really difficult, or like, you know, all the flight service 30 days, is weather patterns. The polar vortex is only really sort of constant and for like this month and a half. And the weather conditions, so it's a combination of finding the perfect window to launch the payload itself, and the conditions at that point is that you have almost no wind at low altitude. So you saw that ANITA was basically ascending pretty much vertically, so the wind at low altitude was very small. But then the polar vortex is very strong at higher altitude, so that it can fly away. So that's sort of like a big constraint. There's those, of course, so okay, there's the weather side of things, and there's the additional side of things that, for example, ANITA 3 got stopped after 22 days because you can see right here, it was going off continent. It was, the trajectory was for the payload that was going towards the sea. And yeah, we did not want ANITA 3 to go in the sea, so we had to stop the flight to go and pick up our data. ANITA 4 stopped for a different reason, and which was our hard drive failed after 30 days. So we have 3 hard drives on flight just to make sure that they're backed up. And hard drive number 1 failed, hard drive number 2 failed, and so we didn't really want to wait till hard drive number 3 failed. And let's see if I have, yes, so these are our 3 hard drives. So the 2 helium drive were actually the ones that failed, and the solid state drive is the one that stayed with us until the very end, but we didn't want to risk it at that point, so we just stopped it and went there to pick it up. If you're wondering why do hard drives fail, is because, well, they don't like being in very, very cold weather for, very, very cold temperatures for a month.
Okay, thank you. Can I still ask? I have 2 more questions, but will be very short. I immediately came with this idea, why don't you go to space? And then I'm actually wondering about 2 backgrounds. And one is, I guess the frequency is too low for the ionosphere to bother you, right? I mean, it's too low, right?
Yeah.
Okay, and then do you actually worry about the satellite constellations?
Right, so, okay, so why don't we go to space? There was a proposal of an experiment called EVA, which was this same radio antennas, but attached to the International Space Station. It didn't really manage to go very far, because at that point you're actually too far out. The sensitivity is not very. Basically you're so far away at that point that you lose quite a lot. Your other question was about satellite constellations, and do you mean, so this main background, this 380, and these are military satellites that are US military satellites that talk to each other the whole time, and we like to do that at the 380 megahertz.
Yeah, because radio astronomers are so worried about the satellite constellations, but I guess that's much higher frequencies, or?
Yes, so these, I think so, because yeah, like our band, so this actually tells you also a little bit of how our sensitivity actually is. So our main sensitivity is between 206 to 700 megahertz. Then it becomes also a lot more difficult for us to see things at a higher frequency, and I think that would be higher.
Okay, thank you.
Are there more questions? Yeah, Nacho?
Yes, yeah, it was a very engaging talk. Thanks, Linda, for that. I remember back in the day there was something called the race array. Is that because I think that R stood for radio and the C was Cherenkov, so I guess it's related somehow to this future experiment. So can you say, was there anything scientific-wise interesting that came out of that, or was it really rather more of a learning experience?
Yes, RICE was more of a proof of concept. See if I can go to ARA. So RICE was more of a proof of concept, and quite a few people that then ended up thinking about ANITA and ARA were part of RICE. But yeah, unfortunately, I wasn't in RICE, so I don't have much more information about that. But it was mainly just a proof of concept. Can you really put these antennas in the ice? How deep you can put them? This is also the other question for ARA. The stations are actually pretty deep. The depth is 100 and 180 and 80 meters. Whereas I think RICE had the shallower radios. Shallower radio antennas closer to the surface, which means you have a reduced sort of sensitivity. Once you go deeper, you of course see more of the ice. But yeah, a lot of the work was done in RICE is then used both in ANITA and ARA.
Yes, okay, thanks. And I had another one related to one of the science cases that you mentioned. So concerning the nature of the ultra high energy cosmic rays and detecting, what's the GZK cutoff and what apparently you made to tell something about the composition of those.
So yeah,
really.
No, not really.
Okay.
So, right. So you, as I showed here, if cosmic rays are mainly composed by protons, then we'll have neutrinos in electron in sort of like two flavors: electron neutrinos and muon neutrinos. Whereas if it just from photo disintegration is mainly electron neutrinos. But even so, we actually can measure different neutrino flavors in ANITA, at least from showery to electron to muon. We have quite a decent, according to simulation, we have quite a decent way of distinguishing them. But once you consider neutrino oscillations, in both cases, you will have a fully mixed, a sort of like fully mixed spectrum. What we do though is that if cosmic rays of this energy were just protons, the flux will be much, much higher. And but this is something we already know. We already know that cosmic rays, at least at the highest energy, from both Auger and the telescope array, we both know that they're not all protons, so they're a mix of protons and higher nuclei, which is probably why we haven't seen as many neutrinos as we first expected in 2006.
Okay, thank you.
Are there more questions? I don't see more hands, so you can ask.
So I cannot raise my hand since I am the host. I have one that is probably very very naive since I am not from the field. In the conclusions, you say that you are going to compare this, like analyze together the sources for 3 and 4. So what will you get from that? So will you be able to remove some of the points? So I am just curious what how is that done and what is the goal?
Yeah, so I think I didn't explain very well this sentence. So it's a slightly different type of analysis. The diffuse neutrino analysis, you're looking at the whole data set and you're making very harsh cuts of and thermal noise to remove backgrounds and any of or saphoids and that. What I mean by source coincidence is that you can look at the at catalogs of GRBs, blazars, and different sources, and then we can look in a very specific direction because. I didn't explain this, but we our directionality is really good. So let's say there was a specific blazar that flared off at a specific time during a flight and in a specific direction, then we can do a subthreshold search in that direction and see if we found a coincidence. In some ways, they're like similar analysis to what IceCube did right here. So I showed it right here. For this Texas, IceCube saw 13 events, but this is not what IceCube saw at the beginning. IceCube saw one event at the same time as this blazar. And so what we did then, we looked back at their data, that everything that came from that specific direction, and then saw on a subthreshold of analysis, there were a few more events, in this case 13, that came from that specific direction, but it was a sort of like second subthreshold search. So instead of finding new sources, we look at sources that other experiments have identified and see if we see an excess of neutrinos or cosmic rays coming from the specific direction.
Okay, thank you. And let me say thanks for the talk. It's been fantastic.
Thank you.
One last chance to ask questions. If not, I want to thank you once again for the talk, and I hope we can have you in Madrid soon.
Me too. Thank you. Thank you for inviting me. And yes, I also hope that I can come to Madrid at some point.
And I think that's all. Bye.
Thank you.
Thank you.
Thank you.
Bye-bye.